Okay, so hi, very good evening, and I'm so sorry I'm late because I'm using my mobile tethering because the current there's some problem with the internet. So please, I will be very sorry if there is any time gap in my video and my voice, etc. So I will be sorry for that because the net is not working right now. Okay, so we are entering into a very important discussion as of today, because what we will be doing in today's lecture is that whatever the videos etc that we have been learning, or whatever the way that we are working now, I would like to explain that what are the books regarding the mathematics of general relativity that you need to learn, number one, and apart from that, how you can relate to the learning of general relativity. What I'm trying to make you a point is that every time we learn that, okay, we need books, manifold, differential geometry, etc. But why will I do that? Obviously to learn the mathematics, but is that mathematics something which is very much related to general theory of relativity? That is what would be the agenda today. So you will get a kind of a complete understanding, get the best books in terms of understanding that, and also you will get to know that, okay, if I learn this amount of mathematics, my efforts is not going into vain. I will be able to learn this amount of general relativity also. So first, I would like to go do a very quick recap because I'm running through my mobile data. So I will come directly to the point. We learned what is, differential geometry. Yesterday, we learned that what is very important is local in nature. So because it is in local, we can use differential calculus, and we can get the understanding of the differential geometry. For a global understanding, what we need is a topology. We go through it. This is a very pictorial and a clear diagram in order to understand that what is general theory of relativity. I mean to say geometric development of thoughts, how things got generalized into straight lines, etc. We also learned that there is a very quick, very important understanding of the, I would say, relationship between differential geometry and general relativity, because the entire mathematics of general relativity is based on differential geometry. So if you're trying to measure the angles, the triangles, the points, etc., the way we used to do in the Cartesian geometry, we will use the same thing, but the mathematics will be a little bit different. For that, we will use tensors, because things will change, because the coordinate and the entire story has changed, but the measurement of the vectors will be invariant. So in order to do that, what we do, we employ tensors. We are going with the tensor lectures. First, second, third, fourth is done. So from tomorrow, again, we will go into the mathematics of tensor. We also saw that what we call straight line in Newtonian mechanics is now called a geodesic, and what we called is a gravitational potential, that's nabla g, that kind, that is what is defined by the metric tensor. We also learned that that is why understanding differential geometry is very, very, very important, because whatever we know in order to learn the geodesics, curvature, etc., pseudo-Riemannian manifold, I have done a little bit of understanding and a lot of notes today on pseudo-Riemannian manifold. I will tell you why, and that is why we need differential geometry. We also saw what is the sequence of your study. First, you need to go through what is called the curvature, because that is the base. Then we will move into manifold. We saw the books of manifold, etc. And finally, we move into differential forms. I also told you what is the best book to select. I'm not going into the details of those books, but what we are selecting right now is an introduction to manifold. And we are not going to the introduction to smooth manifolds by John M. Lee, because this is a little bit more mathematical in nature, and this would help us to understand, get a quick understanding. Okay, so from here, what we do is that we take into a plunge into, I'm skipping those things, into something very, very new, but something very interesting. Now, we understood that the entire physics, I mean to say, whatever we are learning over here, etc., these are, I'm so sorry, this is actually, what is happening? This is actually happening, what is called is a manifold, and we have defined manifold with something which looks local, although it preserves the structure of space-time. So what we see is that there is a very new concept. I won't say a new concept, but I would like to introduce this concept in understanding what it's called a smooth and a differentiable manifold. Now, The question is that whether you will learn smooth manifold first or differential manifold later. I will come to that. That is an individual perspective, but this is very central in our understanding of general relativity. Remember one thing, whatever I am talking about today or whatever you're listening to this have got twofold aspects. Rather, I would say three important aspects. First is that you're going to understand the pure mathematics of differential geometry or curvatures. This is going to benefit to you in your learning of general mathematics, give you an understanding of differential geometry and other things. So overall, what you can say that you are getting one understanding of the pure mathematics in the differential geometry and curvatures. Second thing is that you will now see that if I learn this, I will get this. I will learn this, I will get this. So you won't really feel frustrated, right, in terms of whatever is happening. Third thing is that once you understand the macroscopic level of differential geometry and general relativity, evolution of thought, etc., will become much easier. Not only that, as I told you, once you understand how beautiful light is, you will understand how the darkness is. So when you go to quantum mechanics, which is the microscopic level, things are very small, then you will understand that how predictable these things are and how unpredictable, I wouldn't say unpredictable, but how probabilistic quantum mechanics is. So first you get an advantage in mathematics, second you get an advantage in general relativity, third is that you will now be able to understand a quick contrast between the very big cosmos and the very minuscule small, that is quantum mechanics. So this will give you an understanding. So here is a quick review of what is called a smooth and a differential manifold. So what is a smooth manifold? Smooth manifold is basically a special kind of a manifold that is not only topologically like Euclidean, but allows smooth functions. Now hold on. Smooth function itself is, I would say, a different kind of a concept, which I won't explore here because I will do it later in the class, because smooth function is something which requires a little bit of explanations. And so what is a smooth function? What is not a smooth function? So let us understand that smooth functions means what I have written on the left hand side, those where you can see that take derivatives of all orders. That means it takes the first order, second order, third order, or whatever, without running into any problems. Now, what do I mean by problem? I will come to that later, because this actually speaks of singularity problem, where things get pinched up in a hole, all those things. So let us understand for the for this part of the video that smooth manifold is something which is very smooth. It locally looks like Euclidean, just we have mentioned in the sphere, etc., but which can take all derivatives without running into a problem. This is what is called a smooth manifold. What is a differential manifold? You see, differential manifold is similar to smooth manifold, but it is a little bit more flexible. That means it allows for differentiable functions, which you can take derivative of that derivative of the derivative of the derivative, and you can continue. Smooth functions are always exponential. No, I won't say they are not always exponential. It carries the exponential value. It carries the exponential value, but if you take to up to the c to the power infinity, then it sometimes falls apart. But yes, again, Dhruva, very good question, as I was expecting from you. It carries the exponential, but remember, it is not always exponential. I will come to that later, because this is a good question, but again, if I go into smooth function, I will lose the agenda of today. But yes, you are right on the track. So thank you for this question. So what you see, differentiable function means the curves and functions on a differential manifold must have some kinks or sharps or turns. Now, what do I mean by kinks or sharps or turns? You can very well understand. Okay, let me quickly get my Jamboard ones so that I can at least give you a kind of an understanding of what is a smooth manifold. Oh, where is this share screen? Okay. So in case of a smooth function, I would say, for example, if I take this one, I'm so sorry, should take this one. So smooth function, say for example, this an axis will be something, let us say for example this. For a differential function, it might go like this, but it might have a this and then again goes like this or something like that. So it has got a sharp kink, right? So that is why it is called, it is a differentiable manifold. So that is the difference. I will come to that. Again, it is a part of pure mathematics, smooth and function, but let us understand what is the basic agenda. So the surface of a sphere, when equipped with smooth structure, it is a smooth manifold. So again, the question is that why I'm taking a sphere? Because general relativity deals with the sphere, that is the earth, etc., calculating those curvatures, right? So I'm taking the surface of a sphere. So surface of a sphere is a smooth manifold, where your cube is a differentiable manifold, because you can see that cube has sharp corners. Let us, for the sake of our understanding right now, let us understand this. Now here you see, here is a kind of a quick understanding of the difference between smooth and differentiable. So smooth manifold is a special type of differentiable manifold where all functions must be smooth, which means that they are infinitely differentiable. Now you see, if I go to the previous slide, you will see that it is already written that smooth functions are actually those where you can get the first derivative, then the second, third, etc., without running into problems. That means you keep on and on and on. And that is what exactly this is saying. That what it will happen is that it will go infinitely differentiable. First is the differentiable manifold allows for functions that are differentiable, means you can take at least one derivative of this function. Remember, it is taking at least one derivative. Here you can go infinitely. Smooth manifolds are more restrictive because they require higher level of smoothness. Differentiable manifolds are more general and versatile because they can accommodate, obviously, if it is accommodating the smooth part as well as those kinks and borders. So what is happening is this is actually a very wide range. And in smooth variable manifold, the transition functions are infinitely differentiable. In the context of differential manifold, the transition functions between overlapping charts. That means one is getting overlapped. I will show you the pictorial diagram. This will come when we are dealing with manifold charts and atlases, the smooth and differentiable manifold. From here, you see this is a very important statement that all smooth manifolds are differentiable. First statement. But not all differentiable manifolds are smooth. That means differentiable we will take as I told you here, you see, this is called on the right hand side, you see, it is a generalizer, it is a superset. So that is why I have written that all smooth manifolds are differentiable. But all differentiable manifolds, but obviously they are not smooth. So right at the bottom, you see smooth manifolds are most well behaved, allowing for smooth functions without any kinks or corners. But differential manifolds are more general and allows for functions with some degrees of roughness, where you can take at least one derivative. Here you can take multiple derivatives, right? And it goes on and on and on. Here you can see this will make things clear. Just a second, hold on. Okay. So now you see this is what it is. Dhruba, I think your question will be answered. A smooth function is one that is infinitely differentiable. That is why we get something like c to the power infinity. And differential functional is one that can be differentiated at least once in mathematical forms. So there's c to the power 1. So you see that fx equals to exponential of x. Dhruba, you are just telling, right? You got the answer, that is always exponential. The function is differentiable infinitely many times, and it is derivatives are all continuous. This means that the graph of the exponent function is a smooth curve without any sharp breaks. So I told you that you just need to hold on, you will get the answer to your question. So in summary, a smooth function is infinitely differentiable and exhibits no abrupt structures. That is why I called, you see now that's singularity. Parveen Chunarkar, at infinitesimal part, does a differentiable manifold acts as a smooth manifold? At infinitesimal small part, okay, does differentiable manifold acts as a smooth manifold? Does differentiable manifold acts as a smooth manifold? No, in general, Praveen, the differentiable manifold itself comprises of the smooth manifold. It is a generalized structure. Now, infinitesimal part means what? Differentiable manifold itself is infinitesimal, right? So it won't act as a smooth manifold. We are taking it as infinitesimal. So by default, it is infinitesimal. So further how we can divide it as infinitesimal, right? Okay. Now, here is a question that which one you should learn first. Now, as a teacher, if I tell you this or that, that becomes a problem. I mean to say, but Praveen, I hope you got the answer to your question that it is actually differentiated. So how we can take it further, but it won't act as a smooth manifold. Smooth manifold, as I told you, is a part of that differential manifold, which is a broader one. Now, if I, as a teacher, tell you this, learn this, that I should not do, because the reason is that what I would say, you become biased. But here are a few of the points which will make things absolutely clear to you, and you can decide. On a smooth manifold, the concepts of calculus are much more easier. On a differential manifold that is not smooth, these concepts become more difficult. Smooth manifolds are sphere, torus, Euclidean space. Differentiable is Mobius strip, etc. Application is in physics, engineering, etc. Applications in topology, differential geometry. The smooth manifold are obviously easy to learn, and differential manifolds are more difficult to learn and understand. Now, what I would say is that if you look to Google or go to Amazon or do your search regarding manifolds, the first thing that will come is a smooth manifold. So the number of resources which are available over internet, learning, lectures, etc., are most of a smooth manifold. Differentiable manifold comes much later. So you got the answer to your question. So calculus concepts are easier, differential geometry concepts are easy, smooth manifolds are much more intuitive, and there are more, you see right at the bottom left-hand side, there are more textbooks and outline resources. Smooth manifolds are more fundamental concepts. Here, it is difficult to calculate, and there are very less amount of textbooks, etc. So you now got the understanding what is a smooth and what is a differentiable manifold. This is important before we go ahead and learn this next one. So that is why, so obviously you can start with smooth manifold. Now, here is a question, very central question, that why do we need to study manifold in general relativity? We know that we have seen yesterday also that there are there are books, etc., different areas, etc. But again, the question is that why do we need to study manifold? Is it a pure mathematical concept? It is just we are breaking our head in order to know manifold, that's it? Or it has got some relevance to our target? Because remember, I told you that our target should be right in the front. It is not that we want to become a mathematician, a researcher. Our target is what? Is to understand general relativity. So here is the answer. Read it at yourself. You will be able to answer. Einstein's general relativity is actually the main tool that is used are basically two. One is tensor fields, and the second is Lorentzian manifold. Now, don't ask me what is a Lorentzian manifold. Maybe Dhruva or Praveen, you all know, but I will come to that part later. It is a kind of a manifold. So you understand that in order to know general relativity, the entire space-time, where the entire mathematics and all those equations are going around, it is a manifold. Second, you see, most modern approaches of mathematics of general relativity begins with the concept of a manifold by a four-dimensional, smooth connected Lorentzian manifold. Now you see the second paragraph. It is so important. It tells that more precisely the basic physical constructs representing gravitation is modeled by a four-dimensional, smoothly connected Lorentzian manifold. So you got the hint, right? It is a smooth manifold. So that is why, again, learning smooth manifold before differential manifold becomes easier. Please let me know whether you are getting my point or not, because I can only see you all watching. So you can always communicate with me with a yes or a no. So I hope I can make things clear. Is it not? Please do let me know. It is not that you only ask question, you can also interact with me. So Lorentzian manifold is the basic structure. We are looking into that. The entire physics is depending on that, and it is a smooth manifold. So all the tensor components that we are dealing about, the Ricci, Riemann, etc., which we will explore slowly, of Einstein's field equation whatsoever, are all basically connected to manifolds. That means this is the building. It is a structure on which the entire building is being built. So tensor fields, etc., are manifold. So I hope you got the hint, you got the answer. It is not only that you are studying and studying, but it is something which is connected to general relativity. Also, you will see that a crucial feature of general relativity is the concept of a curved manifold. A useful way of measuring is the object called the Riemann curvature tensor. Now, I would explain in the next class what is a Lorentz metric. First of all, I need to tell you what is Lorentzian manifold, what is a Lorentz metric, what is a Minkowski manifold, what, no, there's no Minkowski manifold, I'm so sorry, it would be Lorentzian manifold, then there would be a Riemannian manifold, followed by a Riemannian metric, followed by a pseudo-Riemannian manifold and a pseudo-Riemannian metric. Remember that in case of general relativity, we broadly deal with just two types of manifolds. There can be a third one, but generally two types. One is the Lorentzian manifold, and second is the Riemannian manifold. Riemannian manifold has been further subdivided into pseudo-Riemannian manifold, which is a kind of an elaboration, you can tell, but these are the two manifolds. Without that, it is not possible. Gravity is taken on Lorentzian manifold, zero gravity or pure mathematics happens on Riemannian manifold. So you remember I told you Riemann was discovering this around 1880 in his dissertation, right? So you see he developed it independently because of the mathematical part. But Riemannian manifold or the pseudo-Riemannian manifold is where the gravity takes place. But pure gravity, which will happen in Lorentzian manifold. Now you get the hint. I was talking in special relativity that it should be invariant, invariant, invariant. Lorentzian manifold only taking care of gravity because gravity is covariant in nature. And Lorentz boost or Lorentz approach is something which is covariant in nature. But you see, Riemannian manifold is not taking care of the gravity part. We will look into that because it was developed as a pure mathematical tool. But Lorentz boost Lorentz manifold was developed on the basis of the covariant theory of gravity. So I hope that things are becoming now very clear to you. So manifolds are basically what we can call, they are very fundamental. They're very fundamentals to general relativity. First is that this specific reason that space-time modeling, as I told you, that entire space-time, Maxwell's equation, relativistic equations, etc., they are actually happening on what? Space-time modeling is happening on a manifold. So manifold helps to represent the curvature mathematically. So the entire curvature, all those things that you see are modeled. We need to have a model, otherwise how do you do that? That is on a manifold. First reason. Second is that whatever tensor that you are using, even if you're learning differential geometry, remember separately, I mean to say just as a pure mathematical tool. I mean, it's no relation with physics, no relation with relativity. Tensor calculus is a pure differential geometry subject. There also you will see that in a pseudo-Riemannian manifold, let M map to X bracket, all those things come up. That is what? That is again a manifold. So tensor calculus, the manifolds provide a framework for tensor calculus. And most importantly, you see geodesics and curvature. Manifolds help define the geodesics, which is actually the curved space-time, which was there in Newton's second law of motion, which I have shown you is a second-order derivative and how the geodesics come in. Now, it is also important for us to understand that what are the different types of manifold which are there. Now, why different types of manifold? Because each of these manifold have its own features. Some will have this, some will have that. We will look into that. So one part is clear that your effort of learning manifold and learning through the books and mathematics is not going in a waste. Either you learn physics, great. Even if you want to learn, I would say pure mathematics, there also it is coming to use. Third, overall, if you learn both of this, quantum mechanics and the probabilistic world becomes much clearer because now you know the light, so you will understand the value of darkness. So what are the manifold? As I told you, that manifolds actually represents a rigorous structure of space-time. It allows us to define concepts such as curvature, geodesics, etc. And manifolds used to formulate the Einstein field equations. So what we can say that this is a mathematical foundation of the theory, and they are very essential in terms of the physical concepts of the theory. So what is the importance of manifold in general relativity? As you now see, these are the three types of manifolds. These are actually the three types of manifold. Now read it gently so that you can really understand all of those. First is what is called Lorentzian manifold. Here you see this is specifically used in Einstein's in space-time in general relativity. I hope somebody, Dhruva or someone is asking that why nature is covariant, why we have to follow Lorentz transformation, Lorentz boost, etc. You see here, this is the reason. That means if you're taking the covariant theory of gravity, the nature of gravity in a covariant nature, then it has to be a Lorentzian manifold. I will show you the photograph also later. So it incorporates both space and time coordinates, and these manifolds have a metric that is indefinite. Indefinite means it can go on for ever. That is why it is indefinite. And Lorentzian manifolds are used to model space-time in the presence of gravity. On the other hand, you see Riemannian manifold, while not directly the space-time general relativity. Riemannian manifolds are essential for understanding. You see the matter in the bold. These manifolds have a metric that is a positive definite. That means that the distance between 2 points is always non-zero. And Riemannian manifolds are used to model the smooth, non-gravitational part of space-time. This is very important. So whenever we will run in Riemannian metric tensor, etc., all those things that you will see, I mean to say from year to year when we move. So the Lorentzian metric is indefinite. Whereas the Riemannian metric, what we see is that Riemannian manifolds, which are essential for general relativity, supernumerals, etc., these manifold metric has a positive definite. That means the curvature, or if you take a sphere, it will always converge. That means it's got a positive definite curvature. And this positive definite will lead to a volume change. We will come to that later. Now you see the third one. What is that? It is called pseudo-Riemannian manifold. This is the specific type of manifold used to represent space-time in general relativity. It involves generalization of Riemannian geometry to include both the positive and the negative signature in the tensor. Now that is why I told you that this is a kind of a that one has got the Lorentzian manifold, what we call it is indefinite. Riemannian manifold is only positive, and pseudo-Riemannian manifold is both positive and negative. In case we need to define a metric using both and positive and definite, how do we do that? This is how we do. We use pseudo-Riemannian manifold. Don't worry, I will come to those manifolds separately one by one and I will explain. Now what becomes more important, that this part is done. Now we come to studying the surfaces and the curves, and as I told that this is the golden book which you should all read. From Euclidean to non-Euclidean geometry, and this is a book which is by Marvin J. Greenberg. If you go to my playlist in differential geometry, you will see I've made an exclusive video expressing on this. Now you might disagree with me, you might agree with me, but I would like to tell you that until you understand the past, you cannot understand the present. So this book not only gives you a mathematical idea, this book will give you an understanding of how actually non-Euclidean geometry came into being. So if you can read through your mobile or whatsoever you are watching, you see Euclid's geometry, everything is being covered. Axiomatic methods, Euclid's first four, all those things. Then the logic and incidence geometry, informal logic, theorems and proofs. Then it goes to Hilbert's axiom, neutral geometry, everything. That means if you are learning this part of the non-Euclidean and non-Euclidean geometry, anything which comes today, say for example, geodesic. It is an extension of maybe Newton's second law or the straight line. Now, if you know that it was during that time that these 2 points, how we measure, there was a restriction, there was a problem, there was a mathematical challenge in order to understand straight line on a sphere. So mathematicians have designed something which is called a geodesic. That is why we call necessity is the mother of invention. So if you now know the past, then you will possibly understand that why these geodesics, etc., came into being. So here is a very, kind of a very honest review. So it's a very dense book, lot of historical fact, proofs are made, and they are very basic overall understanding of geometry. You can also, Vishnu, hi, very good evening. You can also go through this book. This is called Worlds Out of Nothing. And this is also a wonderful book. This is by Jeremy Gray. Now remember, Jeremy Gray, if you watch his BBC interviews, etc., is known to be the professor of, I would say, history of mathematics. Long back, I was born on 1947. So I mean to say he's a terrific books on history of mathematics. So here you can see these are actually the content. I've just given an idea of Poncelet Strait, etc. You can learn a lot of things. So this is basically the idea. So Poncelet and Chasles. I just want to skip those content part, which you can read it out. It's a good book, a little bit different. Proofs are well made, etc. I'm just giving you ideas that whatever the way you want to select the book, you can. This is also another book by Megan I. Dillon. This is called Geometry Through History. And beautiful book. I don't want to go much details into it, but I went through it. Overall, I won't say I've gone through it. So the elements of Euclid, neutral geometry, hyperbolic plane, Hilbert's axioms, up to the algebraic curves, these are all being covered. This is a Springer edition book, right? So this is how. So here is the chronology. I mean to say, if you really want to understand how Euclidean geometry has developed, first go through my Marvin J. Greenberg's book, and then go to this Worlds Out of Nothing. Is this interactive section? Sir, yeah, absolutely. This is an interactive session. Vishnu, you can ask me questions. And Geometry Through History. This is also a very good book. Further, I would recommend also this book, Foundations of Euclidean and Non-Euclidean Geometry. Why am I asking you to take this book? Because this book is divided beautifully in these three parts. Part one, which takes the tools and insights and motivation. Part two, to introduce the student to modern rigorous approach. And the third part is devoted to non-Euclidean geometry. So you see how this book is beautifully designed. First, it gives you that insight that what is this book about. Then it introduces the modern notations, concepts, etc. And then it goes to Euclidean geometry. Now, I would like to tell you that this is a book where I have learned one thing very honestly, I'm going to say, in a very true sense. And I would like to show you to all of you this. I'm skipping the content part. Now, you see, this book actually tells you this. You can read it out. Say, for example, in case of a mathematical proof, etc. also, you want to say, for example, you want to define something. Okay, anything. You want to make a mathematical proof and you want to define something. You see here, it says, let us define a pencil as a sharp tool for writing. This satisfies the criterion of simplicity, which means that any definition should use idea and words that are simple or simpler than the ideas of words being defined. To anyone who does not know what a pencil is, the following definition would be difficult, incomprehensible, or a cylindrical instrument tapering to a conical point as employed by an amanuensis. So what it is actually telling is that it is telling that when you define thing in mathematics, anything that you're trying to define, you should be using simple or simpler than the idea or words being defined. If you try to use words which are so difficult, then people won't understand, definition false. So read the next line. It is simply not possible to define every word without getting trapped either in an infinite process of defining or in circularity. Dictionary definitions are basically circular. This is a golden word, I would say. Dictionary definitions are circular. And he says that it is simply not possible to define every word without getting trapped either at an infinite process. That means if I say I am a man and I'm trying to again define man as say for example Homo sapiens, then again I have to define what is a Homo sapien, and there I use a term which goes back to this. So it is all in a very circular mode. So I mean to say, you see how deep this person goes. This is a book about Euclidean, non-Euclidean surfaces, but even before going to this book, he makes it sure that am I okay in defining a line as a line, a dot as a dot? Because I would again try to repeat, it is simply not possible to define every word without getting trapped either in an infinite process or defining it in a circular. That means it continuously goes on and on. And dictionary definitions are basically circular. That means it gets back to where you actually started. Read the second part, which is equally important. If you wanted to use dictionary in a foreign language, knew nothing of that foreign language and had available a dictionary written totally in that language. To avoid this problem, it is necessary to choose some words as primitive or undefined words in terms of which all other words or systems can be defined. That means it has to be some primitive, very primitive terms, which has not been defined. So the definition of pencil as a sharp tool used for writing satisfies the criterion of simplicity but fails to comply with non-circularity. It also fails to satisfy the third criterion, and this proves often troublesome in mathematics. So last line, what it tells, to sum up, any good definition must be expressed simply, must be non-circular, and must uniquely characterize that which is being defined. I hope this is very deep and you can get it. If you cannot, you can watch it again and again. So the definition of pencil as a sharp tool used for writing satisfies the criterion of simplicity but fails to comply with the non-circularity. That means it is fails to comply with non-circularity means what? It is not becoming circular. And finally, he tells that to sum up, any good definition must be expressed and must be non-circular and must uniquely characterize what is being defined. That means I will be able to define what is that. So today I will take a pause because my net is not working right now. I mean to say I'm carrying with the tethering, which might cause a little bit of slowing down of things. It is already showing the Wi-Fi button from time to time. So I'm studying in the 11th standard. I want to learn space-time geometry, metric tensor. Before that, what are the topics I must be covered? So you can give me advice. I think that you can get in touch with me through WhatsApp or email. So if you want to learn space-time geometry of metric tensor, there are a lot of things that you need to learn. You need to learn multivariable calculus. You need to learn linear algebra. You need to learn a lot of differential geometry. And if you follow this lesson, which we are going today, Vishnu, you will be able to understand, because I'm taking that kind of an approach step by step in order to make you understand about this differential geometry and what are the things that you require. There are many topics. I mean to say, I just cannot tell in 5 minutes time that what are the things that you need to do. But if you want to understand space-time geometry, now don't tell me metric tensor, because metric tensor is again a very generic term. If you tell that metric tensor of general relativity, then it might make a sense. What metric tensor means, any kind of a tensor which makes measurement. So what are the topics? I really don't know, Vishnu, because what are the topics that you have done? So if you're in 11th standard, then you have to go very deep into partial differentials. You have to learn a lot about special relativity. You have to learn something related to linear algebra, also something more about second order partial derivatives and so on. Then you can go. And before that, you also have to learn the physics of special relativity, how things evolve from that. So I would say you have a good amount of job. You can do that. Later, you can get in touch with me. I will elaborate on that. So anyway, so today's lesson was to give you the first idea that why manifold is important, why we are at all doing manifolds. You should start with smooth manifold first and then move into differential manifold. General theory of relativity primarily deals with the Lorentzian manifold and the what you call Riemannian manifold, pseudo-Riemannian manifold also, and the entire understanding of space-time geometry tensor, everything rotates around manifold. So without manifold, we cannot move ahead. We saw what are the books which are required in manifold, and we saw now that these type of definitions are equally important. I showed you 3 books. There are more books. I will come online again tomorrow at around same time, 9 o'clock, or maybe I can shift it to, how do I contact you? Yeah, you can just contact me through my email ID. This is called contact.physicsforstudents@gmail.com. contact.physicsforstudents@gmail.com. I am available in the email, so you can just mention this. I'm just displaying on the screen. So we learned that, but that is not all. Now we will understand that what are the books that we need to learn about curvatures, surfaces, etc. So that, okay, His Highness, many thanks from Ottawa. Thank you very much. I think it is already starting to snow in Ottawa, because I saw a few of my friends really under the snow enjoying the Christmas which is coming. So I think you are enjoying the snow. So then we will learn to the curves and surfaces, and from this again, when we are learning curves and surfaces, what are the books, what are the way we should learn, we will move into how it is connected to GR. What advantage will we get once we understand general theory of once we understand curves and surfaces, how that relates to general relativity. And then we will combine manifold and curves and surfaces and get an idea of Einstein's field equations. This is basically it. So tensors mathematics will go on separately in a class, and this would be an kind of I would say an overall idea, so that everybody can understand things, books, references, things like that. So I think it will be a wonderful thing to do. So thank you very much. Thank you, His Highness, joining from Ottawa. Thank you, Praveen. Thank you, Vishnu. You can later contact me, and those who are watching, please do share. I repeatedly tell, share these videos so that other people, because as I always tell, I'm a small YouTuber, really people don't know that there are exclusive daily classes taking on in general relativity. Back to rain here, snow went to the South USA. Okay, fine. So please do share so that more people can learn, they can join, because you understand this is all free, but we should make a good use of that. People should engage, people should learn more about general relativity, and I'm trying to do my best after my busy schedule from my college, sitting down hours, taking notes, taking the best out of that. Prasant Kumar Padi, thank you, because so that you get benefited. So all these books, all these lectures, etc., making them in a sequence is just for you, so that you learn, and more you interact with me, I think things become quite clearer. So I will continue with that, and by January 2024 I will have a schedule of one day in complex analysis, one day in real analysis, someday general relativity. So I will have a Monday to Sunday kind of a schedule, so that anybody who is interested can come down and participate in that. Good night, Dhruba. Thank you very much for participating, and goodbye to all of you. We'll be back same time, not 9 o'clock. I will try to make it 9:15 so that I can rest a little bit and come fresh. Thank you very much.